Last week we talked about the duality, right, from this page. So, not sure that if you really review it or not, but if you review it, do you have any observations from this duality? Did you observe something? Especially like continuous, discrete, or periodic, or aperiodic? Any relationship between this? Right, so you can see this duality, and it'll be easier for you that to expect. Let me ask you, if there's a signal periodic in one domain, then in the other domain, is it continuous or discrete? Continuous. The signal is discrete in this domain, then in the other domain, it is periodic or aperiodic. Now let's see this duality. Okay, so suppose if the signal is periodic, in one domain, right, continuous or discrete? They'll be discrete. So, which also means, well, same thing. If I have a discrete in one domain, then in the other domain that's periodic. So for example, let's use purple. Like in time domain, that's periodic. Then we can expect in the frequency domain, it is discrete signal. And in time domain, it is discrete signal. Then in frequency domain, that will be periodic. Okay. Let's see this. If I have a periodic in one domain, in the other domain is discrete. In one domain is discrete, then in the other domain that's periodic. Similarly, if it is discrete in one domain, in the other domain, periodic. In this domain is discrete, then in the other domain that's periodic. Okay? So now hopefully that for this dual property, that'll be easier for you to distinguish that this signal is periodic or aperiodic. Okay? Alright. Last week we talked about the sampling. Okay, for sampling, and we tried to reconstruct the signal perfectly, but we know that it is kind of like impossible. But we will try to do our best. And then one way we learned to sample it is to use the impulse train sampling method. So what is the impulse train sampling? I have a signal, and I times a pulse train, the impulse train. Okay, here is the impulse train. Then that is my output. So this times this, what do we have? In this case, we'll get XP. Let's use red. Okay, so here you'll get. So you have a 0 and a TS, 2TS minus TS, and so on. So here is TS, 2TS minus TS. Oh, it should be this point, here. Because this is the signal times the impulse train, that is the summation n from minus infinity to infinity, delta function t minus n ts. I only have values at 0, 1 ts, 2 ts, 3 ts. So here xt becomes nts times the delta function. And then so for here, this is I think I can make it bigger. So here is, this is x of 0, this is x of 2ts, and this one is x of ts. Okay, I only have a value at the sampling point. Okay, so here's the note. We can think of this as a continuous time version of the discrete signal. Okay, now this is like a discrete signal, but it's kind of like a continuous time version. So if you start with this discrete signal, actually that is sampled from the continuous signal. Then you can construct this one, not the x. So to construct this signal, it's just like your original continuous time signal times the impulse train. Then how do we analyze it? Okay, let's see the frequency domain. For the frequency domain, remember, if I have a pulse train, impulse train, what is that in frequency domain? It is still a pulse train. Okay, they just have a different width from ts to like 2 pi over ts. And I also have magnitude 2 pi over ts. Okay, and here let's we put the side here. So let's really take the Fourier transform. Okay, if I take the Fourier transform, actually, what do we have? If I take the Fourier transform, I only have a values when t equals nts. Okay, so if you see the Fourier transform, the Fourier transform of a delta function, just a shifted delta function. Okay, in this case, there should be e to the minus j omega n ts. So therefore, if I take the Fourier transform of the impulse train, then I have summation e to the minus j omega n ts. Okay. Next time when you see the complex exponential, it's like a doing the summation, it is like an impulse train as well. Let's see this summation. If I have an arbitrary omega, okay, for the omega, the frequency, if I have an arbitrary omega, then what do we have? It's like everything 1, next e to the minus j omega ts, next e to the minus j 2 omega ts, and so on. Remember the what is that? The linear algebra that you learned. This summation will be 0, because it is like a wrap around the unit circle. So they will cancel out. So your frequency is almost 0. However, when omega ts is 2 pi k, if it is 2 pi k, which also means the omega is 2 pi k over ts, then the complex exponential becomes e to the minus j 2 pi k n. How much is this? This is 1, right? 1 for integer n. So we will have like 1 plus 1 plus 1 plus 1 plus 1. So finally it becomes infinity. So it is like a delta impulse. So remember that we have a delta impulse only when omega equals k omega s, and your sampling frequency will be 2 pi over Ts. Any questions so far? So in time domain, it's multiplication. Now in frequency domain, I have the term 1 over 2 pi, and they do the convolution. So let's see the convolution here. X, okay, and for the impulse train, in frequency domain, it is still an impulse train. Okay, when they do the convolution, put inside, and again, only when omega, how can I say that? I only have a values, a shift, when I shift 2 pi k over Ts. Okay. What does that mean here, this equation? When I do the convolution, now it's like I have a shift x. So if my x is this in the beginning, what does that mean? Like omega minus 2 pi k over Ts? It duplicates, bum, 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 bum. And also in the negative way. Okay. So when you do the sampling, in your frequency domain, you duplicate your waveform. All right. That means you see that because I do the convolution. Okay, when I do the convolution, so when I flip and shift, then I will duplicate many triangle. Okay, every omega s, I'll make 1. Every omega s, I'll make 1. Every omega s, I'll make 1 triangle. Question so far? So again, that if I have a signal this, I do the sampling, impulse train sampling, I expect in your frequency domain, I will duplicate it. Okay, you duplicate it. But it looks like every time is perfect. Okay, I duplicate that, duplicate that. But have you thought about, I can duplicate this here, 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 here. Just like this one. What happens when we get this situation? There's an overlap here. How come that we have they call aliasing or this overlap? So the question will be like, what is this? What is this? Okay, here we have omega m. But how about this one? This part. This is omega s minus omega m. Right. So the point is here. Omega s minus omega m. If this value is greater than omega m, totally fine, just like that. If not, then we have aliasing. So if omega s minus omega m is greater than omega m, which means omega s is greater than 2 omega m. Okay, so in this case, this is omega s greater than 2 omega m. And the second one is omega s is less than 2 omega m. And finally, your signal in frequency domain will like here. So they will add together. Right. and so on. And here the sampling frequency, that's 2 pi over Ts. Right, so here, this is omega s, right, when we sample that. And however, this is omega s minus omega m. Okay, so first, 1 over Ts, that's called sampling rate. That's called sampling rate. So it's samples per second. And what is omega m? Omega m is the maximum frequency. The maximum frequency in the signal. And normally we call this maximum frequency the bandwidth. So from the picture we see if the omega s minus omega m, this value is greater than the bandwidth, which means the sampling rate, the sampling frequency is greater than 2 times the bandwidth, then there is no overlap. Okay, that is if no overlap amongst the spectrum, the spectral replications. Which we say that if your sampling frequency is greater than your bandwidth, well, your 2 times your bandwidth, then no aliasing. And we call this 2 times your bandwidth the Nyquist rate. So maybe first, second, third. So 2 omega m, we call that Nyquist. The Nyquist rate. So again, if you have your signal in frequency domain, okay, and I convolute the impulse train. Well, or you can think about that my signal is doing the impulse train sampling. That means in your frequency domain, I replicate your waveform. Okay. If your sampling frequency is greater than the Nyquist rate, that's perfect, that's okay. If not, then you have aliasing. If your sampling frequency is greater than the Nyquist rate, then we can recover original signal. Okay, to recover the original signal, how? By the low-pass filter. Okay, we will see the example right away. How do I use the low-pass filter to fill out your signal and get your original one? And in practice, okay, the sample should be greater than the Nyquist rate. You cannot just exactly equal to the Nyquist rate, right? If it is that, it will be like here, right? If omega s is equal to 2 omega m, right? Because in this case, if I use a low-pass filter, it's hard because low pass filter like this, so I can only preserve the signals in baseband. But if you just have your sampling frequency as your Nyquist rate, then it's really hard to cut exactly your signal. Okay, so normally you will get bigger. So they should have a gap between the replica. So between these two, I should have a gap. Okay, so let's see this example. Suppose I have a low pass filter and the frequency is omega s over 2. So let's see the low pass filter. The low pass filter means that in frequency domain, we saw that last week a lot, right? It is a rectangular pulse. Then in time domain, it should be a what? Sinc function. Okay, so sinc function. So if the frequency, the sampling frequency is let me see, 2 pi over ts, then you will get sine pi over ts times t pi t. Now suppose we have this low pass filter. Okay, let's see how do we reconstruct the signal. Okay, so here you can see this is my signal in frequency domain. When I do the impulse train sampling, what happened? This I replicate, or you duplicate this. Okay. And now I duplicate this. I use the low pass filter, so I pass here. Others I will filter out. Then this is your reconstructed signal. So taking the inverse Fourier transform, you'll get your original signal. Okay, let's see how it works. The reconstructed signal in time domain. Okay, in time domain, that means my sampled signal convolve the low pass filter. Okay, so what is our sampled signal here? Convolve your low pass filter. We know that we only have a values at NTS. Okay, so here's NTS. Okay, so again, that for your frequency, sampling frequency, this is 2 pi over TS. And you can see that this cutoff frequency for the low pass filter, this should be between omega m and also this point, omega s minus omega m. Okay, you cannot have that too big. If it's too big, then you get this part. If you get too small, then you miss some signal. Okay, so the bandwidth should be less than the cutoff frequency from the low pass filter, and then they should be less than omega s minus omega m. Okay, any questions so far? Alright, so if we have a flow chart, signal, do the sampling, you get the sampled signal. For the sample signal, then you send it to a low pass filter. You get the reconstructed signal. If I take the Fourier transform, and then from here, if your sampling rate frequency is greater than the Nyquist rate, then you can get your transform inside. So we say that the sampling frequency is greater than the Nyquist rate, or the other way to express the frequency, Fs, that is the 1 over Ts, that's the sampling rate here, greater than 2 times the maximum of your frequency. Then you can reconstruct your signal, and your reconstruct signal is just exactly the same as your original signal. They can express in this term. So x over nts, remember this is your signal, but if you sampled, later on you just see this bunch of sterns. This is xn, and this is x0, x1, x2, for example. So here the xn, this is just numbers. So this is just numbers. And this number is the values at analog signal. At where? The equal spaced instance in time. And this, the purple one, this is what? A sinc function, right? This sinc function is like the interpolating function. Any questions so far? At this stage, you should know that your sampling rate should be greater than how much? Your Nyquist rate. Otherwise, you will get the aliasing in your signal in frequency domain. So your sampling rate should be big enough. If it's too small, later on we will see some examples. If you have too small, when you do the replica, then you double your signals. And when you use the low pass filter, then you cannot reconstruct the perfect original signals. I think here should be TS. Right, any questions? Right, next, let's see how do we use the discrete time techniques to process the continuous time signals. So, so far we just done that for the continuous time signal. We sample it, and then later on we can find the output with a continuous time system. But how about you using the discrete time method and discrete time systems to do it? In continuous time, okay, continuous signal, send it to a system, I got the output. The output is the convolution of your input and also your impulse response. But if I think that first this signal, I convert it to a discrete signal. I use the A to D analog to digital converter. Now I have a discrete signal. With a discrete signal, now I send it to a discrete system rather than continuous system. Okay. So with the discrete system, I got the discrete output, but later on I send it to the D to A converter, and I'll get the output in continuous time. So overall, from these two flowchart, we try to have this part, okay, this system, discrete time system, act like our continuous time system. So we want the system to mimic performance of your continuous time system. What should we do here? First, we need to consider the A to D converter. So what is the A to D converter? That's what we learned an hour ago. I have a signal and I do the impulse train sampling. Then I got the sampled signal, still continuous time. I convert the impulse train to discrete time sequence. So here, this discrete signal is just sampled TS, NTS in continuous time. Okay, but now let's manipulate this. Okay, do something different, and you'll see some fun results. Okay, in our next lesson, or next session, next hour. Let's take a break. First, let's see the A to D converter. Okay, so here, if I sampled the signal in frequency domain, what happened? When I sampled from this equation, you can see that I replicate. Okay, so if I have like a half circle, then I replicate half circle every omega s. Okay, but we can make it a little bit different. So again, how do we find the Fourier transform, or how do we find the expression in frequency domain for the sampled signal? Okay, so here the sample signal, we know that when we take the Fourier transform for the delta function, we'll get the complex exponential. So here's the complex exponential. Okay, we can express two ways, either the delta function or either here. Okay, so there'll be something times the complex exponential. But now let's see, this is a discrete signal. Okay, if I take the Fourier transform, the discrete time Fourier transform, what happens? This one you'll get summation n from minus infinity to infinity. We will say that this is just exampled at the continuous signals every ts. So here we have x n ts e to the minus j omega n. We have the Fourier transform here, and the Fourier transform, like your output, not the output, just convert the impulse train to the dt sequence. Let's see the relationship. Okay, so here the Fourier transform while in frequency domain. Then for discrete signal, the frequency domain, are they equal? Those are the same, right? What's the difference? Omega n here, and here is omega n ts. So this omega, this omega becomes omega ts. So for these two, you don't even need to calculate or find the Fourier transform. Wow, here's a relationship. Omega becomes omega ts. Okay, when we put omega ts, then the omega ts, then I'll get the frequency domain expression for the sampled signal, which means this is our x, okay, in frequency domain. So if I sample it, every time when you do the sample, you replicate your shape, okay? When you replicate your shape, suppose that your sampling rate is greater than the Nyquist rate, okay? But for the discrete time signal, it's the same thing. The height is still the same. The difference is that omega becomes omega times ts. So here, omega s times ts, you get 2 pi. Okay, so like every 2 pi, then it's periodic. I feel that something brown here. This is not s, it's omega m. Here's omega m. So it's omega m times ts, omega m times ts. Do you need to really find the Fourier transform? No. Once you have this, the index, okay, the value becomes the value times ts. Based on here. So if I have frequency response, this, it is not the low pass filter or high pass filter. Okay, the filter looks like this. Okay, it is continuous time. Okay, so for continuous time, in their frequency, we have this. How about that in discrete time? Okay, in discrete time, looks like you can think about that I have a sample it already and then convert it to the discrete domain. Then your omega becomes omega times ts. Okay, so how do you plot HD? Well, in time domain, actually, that is TS times your time domain NTS. Your omega is less than sampling rate, sampling frequency divided by 2. Okay, so here is in continuous time. I have like a filter like this. Okay, so you can think I have a continuous time like a filter, but now I want to convert those impulse train to discrete time sequence. So here I may also have the expression for the discrete time in frequency domain. So how do I plot this one? Similarly, yeah, so in discrete time I still have the same shape, but remember for the discrete time Fourier transform, it is periodic. So actually we have so here is still 1. This is omega m ts, and this will be 2 pi. This is minus omega m ts, and then go to infinity. Okay, so for the y, what is y? We have x and h. Okay, these two, if I times together, okay, so I keep this positive, and here it's negative. So this is positive, here is negative. So for y, let's use blue. Now here's 2 pi, minus 2 pi. This is 2 pi. And here is 1 over ts, minus 1 over ts. And this is omega m ts. Okay, after going through the filter, we got the signal, our output like that. It's in discrete time. Fourier transform. Right, now I need to convert it to the continuous one, the sampled one. So from here to here, again, then you can plot. So how does it look like? We are doing backward, right? Here we have a sampled signals in frequency domain, and then the relationship with the discrete time signal, I just times ts. Now I have this one back to the frequency domain for the sampled signal. How does it look like? I should have the same shape, but the values are different here. Okay, so same shape. So now the height is also 1 over ts and also minus 1 over ts. But this point becomes Wn minus omega m. Here is the sampling frequency. And remember that it is still periodic. Okay. And finally, using the low pass filter, when I get the low pass filter, I can preserve this signal in the baseband. So suppose the low pass filter is this. Okay, and then your overall output becomes -1, 1, omega m, and minus omega m, omega m. Confused, right? Actually, what did we do? Now let's see. First, I have a signal. I have a signal and I sample it. Okay, I sample it. Then since we cannot do this practically, so we need to convert it to the digit signal. So convert the pulses to samples. So this is totally discrete. So for this part, this is the A to D converter. So what do we do? Actually, first I have a continuous time signal. Then I have A to D converter, maybe. Now I transform or convert the continuous time signal into discrete time, and then send it to the LTI system. To the system, I get the output. It's still discrete. So I also need to convert those samples to pulses, and then use the low pass filter to get our output. So for this part, this is the D to A converter. So overall, we try to use this here, this part, all discrete system to mimic our continuous system. This is here, here. So that in the real world, we probably don't, or it's hard to manipulate the continuous time signals. So we convert it to the discrete signals and do something, and then we need to bring it back to the continuous result. Let's see two examples. First, just review. I think you know that how to do this. Consider the discrete time LTI system, and I want to find the magnitude of the frequency response. Okay, so by a discrete time Fourier transform, okay, you take the Fourier transform, you should get discrete time Fourier transform. I have a shift in time domain. What happens? In frequency domain, same magnitude, but I have a phase shift. So to get the frequency response, I have H, that is 1 minus e to the minus j omega 4. Half angle trick. So e to the minus j omega 2. Now I times e to the j omega 2 minus e to the minus j omega 2. Then you get 2j e to the minus j omega 2 sine 2 omega. So your magnitude is 2 times sine 2 omega. So if you plot the magnitude, it's a sine. So, okay, and let's continue. And the magnitude is 2. Here is 0, pi over 2, pi, minus pi over 2, minus pi, and so on. Okay, so this is our frequency response. Now, suppose I have a signal. Okay, I sample it. Okay, this is the input to the system. Okay, how do I sample that? My sampling period, 2 pi over 40. So in this case, let's see, the signal n. Okay, so now it becomes n. So here we need to sample it. Okay, to sample it, we have Ts times, this is a sinc function, sine 10 times t becomes nts, so it's nts 2 pi over 40 divided by pi t, and t is nts, so n at ts. So we get sine n pi over 2 divided by pi n. The sinc function, when we take the discrete-time Fourier transform, what do we have? Sinc function becomes a rectangular pulse, and since it is discrete time, so I'll get periodic in frequency domain. So the x, it's either 1 or 0. So when the frequency is between 0 and pi over 2, it's 1. Otherwise, it is 0, like pi over 2 to pi. Pi over 2 minus pi over 2. And here's a pi. So here's pi minus pi. So I will get another one, and so on. This is our input and our frequency response, the system's response. Now we can find our output response. For the output, we times this together. Okay. So from minus pi over 2 to pi over 2, I got two small mountains. So here's pi over 2 and minus pi over 2. Here. All right. So when x is a sinc function, now here's the output. But when the x is a sinc function times cosine, what does that mean? That if I times cosine in one domain, in frequency domain, what happens? I have a half of that value, and then I separate to pi and minus pi. Oh no, depending on this, I shift. So suppose my signal is a sinc function times cosine. In frequency domain, I will shift. Okay, same thing, but I will shift to the right and shift to the left. So the x will be 2ts sine. Okay, 5t will be 5 times nts. So n times 2 pi over 40 divided by pi t. So t is n times ts. And then cosine. So now that's we're doing sampling. So 15. Your t becomes n 2 pi over 40. So overall, you get sinc function so pi n, and then cosine. So what is the Fourier transform? We have sinc function times cosine function in time domain. Frequency domain, we can do the convolution. So let's do the convolution. It'll be 1 over 2 pi times, we have 2. And for the sinc function, my frequency domain will become a rectangular pulse. I should use pink. So this is 1. Here is pi over 4 minus pi over 4. And we need to convolve the cosine. For the cosine, 3 pi over 4. So I should get 3 pi over 4 something minus 3 pi over 4 and then here's pi, here's minus pi. Right, when they convolve together, what do we have? I may expect here I have a pulse, Here I have a rectangular pulse, right? So here's 1, 0, pi over 2, 3 pi over 4, and pi minus pi 8 minus pi over 2 should be in the middle, minus 3 pi over 4. In this case, this is our x. Here is still our system response. If I times together pi over 2 to pi, pi over 2 to pi, I only get this part and this part. Okay, I only have these two half circle. So here's my result. So here is 0 and height is 2. Pi over 2, 3 pi over 4, and then pi. Minus pi over 2, minus 3 pi over 4, minus pi. Okay, so that means that if my signal is like this, I'll get this 2 as our output. If my signal is here, this is the sampling rate. So first let's analyze the x. Okay, if I sampled 2 pi over 20, we have Ts times sine 10. T is 2 pi n times divided by 20. So n pi over 20. 2 pi divided by pi nts 2 pi over 20. You get the sinc function, sinc pi n over pi n. That is just delta function. So delta function in time domain. What do we have in frequency domain? In frequency domain, how does it look like? Think about the possible theory. If I have a delta function in time domain, what's the Fourier transform? Exponential. Intuitively, delta function in frequency domain, possible theory, this delta function is like going to infinity, right? So in frequency domain, possible theory, it should be all flat, right? Because the magnet, the area under the area will be also infinity. Okay, so in frequency domain, okay, there'll be all 1. But actually, it's from minus pi to pi, and then repeat. Okay, so in that case, your output is just your system's response. Okay. So then we will talk about the other signal. If my signal, this, send it to the system, same system, what happens? If I have a signal like this one, so let's sample it. This is the sampling rate. Okay, if I sample, let's see what happens. So T becomes NTS, that'll be sine. Um, 10 times NTS, 3 pi over 20, divided by pi times NTS. So I can cancel out this one. You get sine 3 pi over 2 times m divided by pi n. Okay, let's check. What is the Nyquist rate? In this example, the Nyquist is 20. And then let's see our sampling rate. Sampling rate 2 pi over Ts. Here's 3 pi over 20. So you have 40 over 3. Actually, this is less than the Nyquist rate. Remember what we learned today? If we don't want to have any aliasing, then my sampling rate should be greater than the Nyquist rate. So this is opposite. So we have aliasing. So what does that mean that we have aliasing? Let's plot the signal in frequency domain. Okay, so in frequency domain, it becomes here we have pi over 2 and pi minus pi over 2 and minus pi. Got 1, but here become 2. And then they repeat. So here is 2 and 1. Remember that it should be the sinc function. It should be like a rectangular pulse, but if the sampling rate is greater than the Nyquist rate, then I should have this right. However, now I got this part. So that's why here we have 2. And then this is 1, and here the overlap I have 2 and 1. So if I have an aliasing, then our output is still the system's response times the signal in frequency domain. In that case, I double it. So for these two regions, I double it. So your Y is not just the same half circle. It becomes this is from 0 to pi over 2. But pi over 2 to pi, I. So 0, pi over 2 to pi minus pi over 2 to minus pi. This is 2 and 4. Now let's quickly go through what we have done. The discrete signal, okay, here the index is like 0, 1, 2, 3, 4. But the right hand side, this is the continuous signal, but I sampled every TS. So you can see that this xn, suppose this xn is this. Okay, this is n. Alright, so there will be 0, 1, 2, 3, 4. The index is 0, 1, 2, 3, 4. For the right hand side is continuous, so I sample that. There will be 0, here is TS, this is 2 TS, 3 TS, and so on. This is minus TS. Okay, so their index is a little bit different. Okay, the width here is like a TS, but here the width is like 1, 2, 3, 4, is 1. Okay, now for the continuous time signal, I take the Fourier transform. I can also think about that discrete time signal. I take the discrete time Fourier transform. Okay, and for this discrete time Fourier transform, they have something in the relation to the continuous time. Okay, how? For this discrete time Fourier transform, it is the same as our sampled continuous time signals in their frequency domain. Omega becomes Fs times omega. Okay, just like here. Now we put Ts. Remember, Fs is 1 over Ts. Okay, so for the sampled signals, okay, actually, how do we get this sampled signals in frequency domain here? Because did I write? Okay, I can write here. Because we derived that last week. Okay, now we change the OTS 1 over TS to Fs. Then we get here. Alright, but we can also think about our sampled signal. Okay, our sample signal is the signal times the impulse train. Okay, so when the signal times the impulse train, I only have a values when t equals NTS. So this means the summation x, when every ts I'll get the value. Okay, so it should be NTS. And this is the discrete signal. Okay. But to get the Fourier transform for the sampled signal, okay, I can, this one, you take e to the minus j omega t. Again, only when t equals NTS, I have a value. So there will be summation. Then we can compare these two. Let me see. Well, before we are doing the comparing, so this is the Fourier transform for the sampled signal. Okay, I changed the TS to FS. Now you can compare this expression with the discrete time signal through the discrete time linear time invariant system. So for the discrete time signal, we do the discrete time Fourier transform. So this is the discrete time Fourier transform. When you compare this to, you can say this expression, this equation. How can we get the frequency domain for the sampled signal? Okay, we can use the property, because it's a signal times the impulse train. So in frequency domain, I do the convolution. When I do the convolution, I should get so the frequency domain for the discrete signal, actually it is the frequency expression for the sampled signal with omega times fs. Right, so if I sampled in time domain, then we will do the replications in frequency domain and also periodically. So we have replications in the frequency domain and periodically. Spaced every integer multiple of 2 pi fs. Same as here. Okay, so the compression by the fs will cause the replication in the discrete time Fourier transform to occur every 2 pi. So the discrete time Fourier transform is periodic with the period 2 pi. We can also check that, and we did that before. Okay, so omega plus L times 2 pi. The L is just an integer. So if you can see, that's signal in the product your basis minus j omega becomes omega plus L 2 pi n, and this is the signal in the product your basis times e to the minus j 2 pi to the ln, but e to the minus j 2 pi, it is 1. So that's why this is periodic with 2 pi. Next, let's see the sampling to the sinusoidal wave. Let's see what happens for this. So this is the sampling and analog sine wave. Suppose my signal is sine, or the combination of sine and cosine. Okay. Then Fs is the sampling rate. So Fs is the sampling rate. Now my signal, and also my signal. Okay, I sampled. So you can either write NTS or N over F of Fs. Okay, so since our signal is the complex exponential, the omega d means the discrete time frequency. Okay, d means discrete time. So here we can write it down. This is discrete time frequency. Okay, that's their relationship. Now we have a relationship between the discrete time frequency variable and also continuous time variable. This relationship is omega d equals omega ts, or omega over the sampling rate. Now consider this signal is still exponential, complex exponential, but at plus L times 2 pi fs. Here there's no t inside. Okay, in your note, in your handout, you need to cross out. I only have everything times t. And L is the integer. So if I sample it, I have XL so T becomes NTS or N over Fs. So it will be e to the minus e to the j omega n ts times, that's the first term, and the second term we have e to the j l 2 pi fs n ts. So keep the first term. Oh, we can rewrite j omega ts. Omega times ts is the discrete time frequency. N e to the j l n 2 pi. This term is 1. So e to the j omega d n. This means that any two analog frequencies separated by L times omega s here, because this is omega s, separated by L times omega s, may get mapped to the same discrete time sine wave. We will see an example in 1 minute. And also because the discrete time frequency is omega over fs. So this also tells us any two continuous time sine waves separated by L times omega s yields two discrete time sine waves separated by L times 2 pi. And this gives you the same discrete time sine waves. Let's use the example to explain the notes here. Okay. If I have a signal cosine 3t, cosine 6t, 7.5t, 9t, 10.5, 12, and now I sample it. Sampling rate. We can plot the magnitude of discrete time Fourier transform. Okay. So first we sample it, okay, with 2 pi over 12. Let's see the first signal, cosine 3t. We need to check the frequency, sampling frequency. First, what is the sampling period? 2 pi over 12 means the sampling frequency is 2 pi over Ts, that's 12. What does that mean, 12 here? This is the sampling rate, right? So the sampling rate should be greater than the Nyquist rate, which is 2 times the frequency, the bandwidth of that signal. So you can only see the highest frequency. Okay, the highest frequency is 6. Otherwise, when we sample that duplicate, well, we have aliasing. We can check this. For example, cosine 6t okay, I sampled t is NTS, which is n times 2 pi over 12. Okay, here we get cosine 6 times n times 2 pi over 12. Okay, here we get cosine n pi. Cosine 7.5t, I also sampled at n times 2 pi over 12. Now what do you have? Cosine n times 7.5 will be 15 over 2 times 2 pi over 12. This is cosine 5 over 4 n pi. We want to see this between minus pi to pi. Okay. So here, this is also equal to cosine 5 over 4 n pi minus 2 pi. So you'll get cosine minus 3 pi over 4. Or it is equal to cosine 3 pi over 4n. And cosine 90 if I sample we get cosine 9 n times 9 times 2 pi over 12. It is cosine 3 over 2 n pi. So I want the frequency between minus pi to pi. So this I can think about like minus 2 pi we get cosine minus pi over 2 n, which is just cosine pi over 2 n. Cosine 10.5 t. If I sampled with this sampling rate, because cosine that be n times 10.5 means 21 over 2 times 2 pi over 12. So this becomes cosine n times 7 pi over 4. So let's move that to minus pi to pi. Minus 2 n pi. We have cosine minus pi over 4 n, which is equal to cosine pi over 4 n. And we have 12t and 3t. Oh, I forgot to get the 3t. Cosine 12t then we sample at 2 pi over 12. We get cosine n times 12 times 2 pi over 12, which is cosine 2 n pi, which is cosine 0. And the next one, the last one, cosine 3t. We have cosine n times 3, 2 pi over 12. That'll be cosine pi over 2 times n. Because we know that the discrete time Fourier transform is periodic. Normally we will see the spectrum from minus pi to pi. Okay, so after, well, beyond the minus pi to pi, they will just replica. Okay, because it's periodic. So for this, we can plot the spectrum. Here's the spectrum. Oh, here should be pi, 2 pi, pi, 2 pi. So like cosine 7.5t, they will drop to here. And cosine 9t, let's see, cosine 9t, it should be 3 n pi over 2. Okay, something here, but that's aliasing. They will go to this to here, and also cosine 3t. It is also like n pi over 2. So that's why I have a pi plus pi. 1 pi is from cosine 90 for aliasing. You know that for the Fourier transform, if I have a cosine, I should get this too, right? The Fourier transform, right, here. If I have enough sampling rate, then they will repeat here, 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 here. Okay, but if the sampling rate is less than Nyquist rate, the next round maybe here is the center. So they will put this one and this one and this one. That's why you have this duplicate like here. Remember? Okay. So that's why that your sampling rate should be greater than the Nyquist rate. Now suppose last one. This signal is passed through the discrete time linear system. Then I want to see the frequency response. So for this system, we know from this expression we can get the frequency response A. That's y over x 2 minus 2 times cosine omega. So 2 times 1 minus cosine omega. So it looks like like this. This is 0, and here I have pi over 4, pi over 2, 3 pi over 4, and here's pi. Similarly, minus pi over 4, minus pi over 2, minus 3 pi over 4, and minus pi. Right, next week we will see more examples with aliasing, which means that your frequency, your sampling rate is less than your Nyquist rate. And how do you plot it? Okay, maybe that will be also in your quiz or the exam, that you need to plot the magnitude of your discrete time Fourier transform. In that case, how do you deal with those aliasing? Okay, any questions so far?